Okay, so let's start this week with the first lecture on revising current carrying conductors and Ohm's law to start with. We have already seen, we already know from our high school days, okay, that Ohm's law is a phenomenon, especially with conductors, and that gives rise to a property, the electrical property of the material, or the conductivity, or the resistivity. In a typical experiment, you apply an electric field V and measure the current I, and then it should come out as a straight line. And let's say consider a voltage V across a long solid cylinder of copper, and then you will get a current. And we know that you will get a graph like that. And what does the slope give you? Slope give you the 1 by resistance, because we know V is equal to I R. And so R is the resistance. Now, is the resistance a property of the copper material? No. Of course, it depends. Obviously not, because since it depends on size, shape, and geometry of the thing that you have chosen. Okay. So, and we know that the resistance R depends upon the length of the conductor and the cross-sectional area through this rho, which is the resistivity of the material. Okay. So rho is the resistivity of the intrinsic, and this is an intrinsic material property. Now the question is, what is the microscopic origin of this resistance? That's what we're asking. So a good metal, we know, follows Ohm's law. Okay, and the material property we now know is conductivity or resistivity sigma. Conductivity is just inverse of resistivity. So let's take that copper cylinder, and if the cross-section area is A and there's a current I, and I can apply an electric field which is V by L, and then I can plot, instead of I and V, I can plot E, the electric field, and the current density I by A, current density J, and that also should be a nice straight line. Okay, and the property in sigma is the conductivity. Typically in the community, one refers to it as omega inverse centimeter inverse, or resistivity as omega centimeter. Okay, so and J is sigma E. Okay, so for a homogeneous material. So that's my Ohm's law. Now, how does this current flow? Let's look at that. Normally we put a battery, which is nothing but a force which is per unit charge from, okay, so that is, it pushes a charge into the, okay, if I connect it, then that's the one which forces a current into the conductor. Now, what is, so the role of this force, which is electric field also is a force per unit charge, and this F of S, okay, which is we call the source of the force which pushes it, and then what is the role of E and what is the role of F of S. Okay, that's something we're going to worry about in this chapter, because this is the source of EMF, okay, electromotive force, which we know. But we'll have to be clear of many things before we're doing that. We'll ask a bunch of questions. Normally this is so popular and we already know so much that either you don't ask these questions, and or these questions remain as some kind of common confusions, okay? And hence let me ask those bunch of questions. So what is the role of E and F of S in the flow of the current around the circuit? When you connect it, it's not connected that nicely. There's some loosely hanging wire. Now, what is the source of this E? And in any of this connector or inside, are J and E uniform? Okay. Even if the cross section is, let's say, odd shape, will the E and J be uniform? Then how long does it take for the news of the charges that have been pushed here to reach, let's say, other parts of the circuit? Okay, that one charge has been pushed and soon we'll have a current flowing in the circuit. How long does that take? That's the how much time does it take? And that will clarify the role of the battery and the electric field in the circuit. That's okay. So we'll answer some of them one by one slowly. Let's take the Ohm's law. Two examples. Okay. So example, let's say 8.1, in which a cylindrical resistor of cross section area A and length L is made from a material with conductivity sigma. Now we can consider this. So I have deliberately taken a resistor in which this is odd shape, except that the cross section is the same everywhere. Okay, but it is not nice rectangular, a nice cylindrical circular cross section. Okay. And the question is, if the potential is constant over this face and the two ends, and the potential difference is maintained between the ends is V, what current flows? Typical high school question. Okay, of course you can answer immediately. If there is a current I, then this is J into A. Okay, and J is sigma E into A, and sigma, what is E? Is V by L. Okay, and hence sigma AL by V, and hence I can write down that is V is equal to Ri, and R is rho L by A. Okay, so that's quite easy. But okay, let's take another example, which is in which I now change the geometry. This is quite regular. So two long cylinders of radii, let's say A and B, are separated by a material of conductivity sigma. Okay, so that is inner and outer. And if they're maintained at potential difference V, what current flows from one to the other in a length L? It is filled with, again, the in-between material is filled with a conductivity which is sigma. So assume, we know how to solve this. Assume lambda is the charge per unit length for the unit cylinder. Calculate the electric field. It is easily calculated by a Gaussian surface, which is lambda by 2 pi epsilon s by s. And then I is j dot dA. dA is also pointing in s hat direction. E is pointing in s hat direction. And hence I is sigma lambda by 2 pi epsilon naught s dA. And I can write down this as sigma by epsilon naught lambda L, right? Well, this, in the meantime, I can also calculate the potential V. Potential V is minus from B to A, E dot dl, E already I know, and dl I know, okay, is from here to here, and hence it is lambda by 2 pi epsilon naught ln ln V by A. Okay, so I know I know V, and hence I should be able to write down I in terms of V. Okay, and that gives me, so the inverse of this is the resistance. So R is log of B by A 2 pi sigma L. So V is still IR, our old high school physics Ohm's law. Ohm's law is, by the way, is not a law in the sense we have learned other laws. It's just a shortcut for observation of phenomena for a certain type of property and material. But be that as may be, okay, so R is different in different geometries, of course, but V is equal to I by R. But one thing that while solving this, I assumed that irrespective of whether this is this odd shape, the J and E are uniform. Only then I could actually write this down. That was my implicit assumption. But let's ask that question. Is it uniform really? Okay. So is E and J uniform here? Let me take this question forward. So we'll worry about this uniformity in a homogeneous ohmic material. All right. So let's take first. So is E and J uniform? Let's take the same example, okay, of that conductor. Though I'm making a broader point, but let's take the same example and then ask for a steady current and uniform conductivity. Okay, we know that divergence of E I can write down by, since it's a uniform conductivity, I can take sigma out of this. It's just a scalar. So J by sigma is E. So I can take sigma out. Divergence of J. Since it's a steady current, divergence of J must be 0. We know that from continuity equation. And hence, divergence of E is 0, which means there is no rho in the body of the conductor. Okay, so, but it can appear at the surface. Okay, only thing it says that there is no rho, there is no volume charge if the conductor is uniform and if there is a steady current flowing in it. Okay, so therefore we can say that Laplace equation is valid for homogeneous ohmic material carrying steady current. Okay, and so what about boundary conditions? I know that is Laplace equation is valid in the body, in the region of interest, but the boundary conditions. So the boundary conditions, we said that this is held, the two ends are held at constant potential and a potential difference of V is maintained. So I can as well say that this is 0, this end is 0, and this end is V naught. Okay, so left face, let's set 0, and right face is V naught, so that the potential difference is V naught. What about the curved surface? On the curved surface, of course, there is J dot N is 0. Why? Because there is no charge leaking out to the surface of the conductor. And hence, E dot N must be 0, which means del V by del N 0, whatever be it. And hence, we have Laplace condition satisfied. We have the boundary condition known, and we can, whatever solution we get will be a unique solution. Now, for this simple thing, can I guess that will be unique? Can I guess it? Of course I can. Okay, and the solution that I guess is, let's say V of Z, V naught by L into Z, K, and it fits this description. Okay, so del square V will be 0. Okay, there will be no rho, and the boundary conditions are valid. Okay, so that is a solution. So in that case, I can write down my E minus grad of V, and that is minus V naught by K, which is indeed uniform. Okay, so now I've proved that it is uniform. I've not assumed it. Okay. So, and let's, the role of E becomes important in current conduction. Suppose I did not, this is a vacuum between the two plates, between the two regular plates. And then just try and finding out the electric field all around. It's so tough. It's not possible analytically. There will be fringing fields and fields will be. But as soon as I put a conductor between these two, okay, then J and E become nicely uniform irrespective of the cross section and shape and size. Okay. In fact, the wires that we use are all going around in different shapes, but J and E in those conductors are uniform and become smooth and uniform. So that is the role of E in actually controlling the current conduction. We will discuss more about it. Let's take a microscopic view of conductivity from here. This, in some sense, I've discussed while discussing the case study on Hall effect in one of those classes. Okay. So, in fact, we had also mentioned the rho, the resistivity variation. It can vary widely. Okay, this 1 micro-ohm centimeter is for typical good metals. We've got very good metals, and 10 to the power 18 is for very good insulators. So copper is, let's say, 10 to the power minus 6 ohm centimeter, or 10 to the power minus 8 ohm meter. Okay, and glass, typical glass we use insulator, which is 10 to the power 10, and fused quartz is 10 to the power 18, extremely high insulator. Okay. So, but of course we have superconductors, which is zero resistivity. All right. I'll discuss this later in this chapter, a little bit of electrodynamics of superconductor. 10 to the power 14 is diamond. Okay. And what about silicon? Silicon, of course, is a semiconductor. It can vary depending on the composition, the impurities in it. Okay. Let's consider let's say something like a copper, block of copper. Okay. And it's a very good conductor. And let's say it has n free electrons per unit volume. That's the concentration. And then there is I've applied an electric field and there's a current flowing. And then what is the flux of electrons to the right? There is number of particles crossing per unit area per unit time. That is the flux. Okay. And so what is that? That will be, of course, n. This n is the carrier concentration. And if I take dx, then n dx is the amount, the charges flowing in time dt across this dx, across this area. And that is n of dx. So I can generalize this to saying that the current density is typically flux. Flux is, of course, n into the velocity. And what they're carrying, flux of current, meaning current density is charge. And hence, I can now consider that these particles are electron. And in 3-dimensional, let's say the velocity is v. I'm generalizing. And hence, the current density is minus E n into v. N into v is the flux and is the charge. Minus E is the charge, and that's the current density. So now for a steady current on application of a electric field, E, the net velocity vector must be also constant because this current is steady. This is not time dependent. Hence the velocity also must be constant. Now the net velocity, okay. But on application of electric field, should not the free electron be accelerated? Should not be accelerating. If it's accelerating, then shouldn't the V be changing with time? Why is the V constant? That's a question that we have asked earlier. But why would they move with constant velocity? Okay, of course, we have discussed that a little bit earlier, but let me restate it. Okay, the simplest possible model of current in a conductor, okay, would be that there are free electrons, of course, and they are accelerating when a field is applied. So then dp by dt would be this is the force minus EE. And if that is true, then the P would be changing with time. I've just integrated over time, assuming that P is equal to 0 to start with, minus EET. And if I now write down my J, P by M, okay, then minus NEET by M, then the current should be actually changing with time. It should be linearly increasing with time, if this is true. Okay. So J would be, but that's not our experience. Okay. J, if I apply an E to a metal, then it produces a steady current. So obviously, there is something else going on. Okay, and we know that the motion of the charge carriers inside the metal is impeded. Okay, that is, the medium offers resistance to its motion on the field, and the source of this resistance has been a mystery till we understood a lot of quantum mechanics of solids and statistical physics. Almost by 1950s, it was becoming clear what is the source of this resistance. Okay. But the simplest model came in 1900. He suggested that the free electrons in metals behave like atoms in a gas, which undergo collisions, okay, while moving through the solid. Now, what is actual source and origin of that collision? That was not clear, but there must be some collision. Otherwise, the current should be increasing as a function of time. Okay, so now collisions with what? Now we know, okay, only now that this collision happens with defects or impurities or quanta vibrational energy of the atoms. Atoms are oscillating, and So that vibration, the electron can collide with. By the way, electrons don't collide with atoms. They collide with the the vibrational quanta of the vibrating atom. Anyway, that discussion is a separate discussion. Okay. So between two collisions, let's assume that there is a for which it's accelerated, and that is tau c. Okay. And the concentration of free electrons, V is the average velocity, and the concentration of free electrons per unit volume. Okay. So now this is considered as the simplest possible model of a metal, and that is the Drude model, which we have discussed while discussing Hall effect. So consider an average free electron moving under field inside a conductor. It collides on an average time, let's say collision time tau c, and within that time, whatever momentum it gained, it loses. Okay, and hence it can be modeled as dp by dt. Of course, there is a force because of the electric field, but it loses the momentum gained in time tau c by a collision, by a random collision. All right. And so this is the force, and this is the loss of momentum after average collision in time tau c. That's the, now in steady state, of course, we are applying the E and holding it for a long time, so that the steady state is reached. And the rate of change is, of course, then is zero, then dp by dt is zero. And so I can now set this equal to zero, and that will allow me to calculate what is this V if it is under steady state. So the V is then simply minus E tau C M E. So E tau C by M. So here, what the first thing to note is that the velocity is a constant, of course, okay, and is not changing with time, constant with time, and is directly proportional to the applied electric field. And this quantity is called, this is of course called the drift velocity, because this is the direction in which the electrons are drifting when applying an electric field in that direction. Okay? They have thermal motion in all kinds of random motion, but if apply an electric field, then on an average they give drift in the direction of the electric field, and this proportionality constant, okay, is called the mobility. So this is the drift velocity, this D is for drift, and then this quantity is called the mobility, okay, which you can see that if mass is small, mobility will be large. If the collision times are large, then the mobility will be high, because if it doesn't collide very much, then it will be high. So that sort of mobility, and it can be measured through Hall effect experiment. So now then I can write down the current density J is minus En Vd, and so N is square tau C by M E. So J is proportional to E, and this is then, I just replaced Vd here, okay. So this quantity is then, J is sigma E. So that is my sigma, N is square tau C by M. This is the simplest possible model for conductivity of a conductor. It's in terms of the electron concentration, okay, and the one theoretical parameter called the collision time, but any tau, as I said, can be measured through Hall effect experiment, and both N and mobility can be measured through Hall effect experiment, and that is my sigma. So note that the drift velocity is like a terminal velocity. Okay, that is, for example, the raindrops hitting us coming from high above. Okay, they hit us with a terminal velocity. If they were not having air resistance and they would be accelerating under gravity all the while, by the time they reach us, they will have speeds like bullets. Okay, so but they achieve terminal velocity after dropping for some time. Okay, because of the air resistance. So similarly, you can view the drift velocity is like a terminal velocity because of the collisions which impede the motion of the particle inside. Okay? And as I said, one can measure mobility, and hence drift mobility from Hall experiments. It can be actually a very small velocity. This of the order of meter per second. Now, is this the velocity by which we can expect the current to travel to one end to the other as soon as they switch on? How long does it take for the news that the battery has been switched on to the other part of the circuit? So when does it know that now a current will be arriving? All right. So is that the velocity of the drift velocity? Obviously not, but we'll discuss that. Okay. And next. Let's discuss how much. What is the? In other words, I'm asking how quickly steady state is achieved. Does it depend on drift velocity? Let us make an estimate. Once a charge is pushed into the solid, say by an EMF source like a battery, then the charge neutrality has to be established. Now, how long does that take for the charge neutrality to be established? Okay, because we know in electrostatic condition, if I put a charge inside the metal, then the metal goes, then those charges go to the surface. How long does that take? Okay, is a similar question. We know that the electric field, due to if there is some accumulation of charge somewhere, then electric field will make it move away. Okay, so and it helps achieve this neutrality by moving the charge out. So as the steady state is achieved, we know in steady state condition there should be no volume charge density in the body that we have just shown. Okay, so let's look at the dynamics from the t is equal to 0. When I introduce some rho charge, volume charge into the conductor, then of course I know that this should be the dynamics of it will be controlled by the continuity equation. There is no sources or sinks, so del by rho t will be minus divergence of j. But I know this is the conductor, so j is sigma e. So I can replace j by e here. Okay, there's minus sigma e, and sigma is homogeneous, so I can take it out, and this divergence of e. Now divergence of e should be equal to rho by epsilon. Epsilon is the permittivity of the medium, and rho is the charge. Okay. It's a pretty general argument. Okay, so it could be anywhere. So del rho by del t. Then what I have done is I have now taken sigma here, such that this is of course charge, and this quantity has now the dimensions of time. Okay, that we know, epsilon by sigma. So, and hence I can write down the solution, assuming that rho at t is equal to 0 was some rho naught. Okay, and then this is the first order equation, and of course there's a minus charge, so it will exponentially decay, and the decay constant is epsilon by sigma. Okay, and this is, I put a d as a subscript because this constant, this time constant, is known as dielectric relaxation time. Okay, so that is epsilon by sigma, dielectric relaxation time. So this is an important quantity. Now, what is this coming? Once I apply rho, there will be field, and the field will be trying to, there are two things that field can do: polarize the material, or conduct the charges if there are mobile charges. Okay, so this quantity tau d seems to be a competition ratio between the polarization and conduction. If this is conduction is pretty high, then this time constant will be controlled by sigma. If sigma is low, then this will control the time constant. All right. So let's estimate that for a typical metal. For a good metal, okay, rho is 10 to the power 8 ohms, ohm meter, and so tau d is of the order of 10 to the power minus 16 seconds. Okay, and for an insulator, it can be almost 100 years. Okay, because sigma is very low. It's 10 to the power, for example, in fused quartz is 10 to the power 18. So if you, and this is of the order of 10 to the power 10, minus 10. So this will be, I don't know how many years. Okay, so which means if we, in an insulator, if we introduce a charge then the charge is going to remain there. It's just to polarize the medium around it, but it's not going to go away. Charge neutrality will never be achieved. But if in a conductor, you put an extra charge, charge neutrality is achieved in almost instant time. Okay. So another phenomena which we can easily explain with this is the Joule heating. Okay. That we know that in conductor that the current is moving, then it gets heated up, and that's how, and that is I square R. Let's see it from this microscopic model. So that as a result of collisions, okay, that is the power lost, joules per second, is sigma E square. That's the Joule heating. So work done in time t, we can write down as, let's say, this is a thermal velocity, and I have increased the velocity by E T by M, right? And then I had already had MV, okay, so this is the difference, all right? So I can write down, so MVTH, and so this is delta P squared by 2M, and I can write this difference would be E square T square by 2M. Now, what is the probability that time T has elapsed since the last collision? As times, suppose there is no collision and the particle is traveling, okay? Now, as the time goes by, the probability that it will, that it has not collided is exponentially going down, okay? So probability that it has not collided at time T, okay, at any time T goes down, of course, minus T by tau C. That's how tau C has been actually defined, okay? And the probability that it will collide in the next small time dt, that is how much? Is dt by tau c. Okay, within the small differential time dt, it is going to collide. So the probability that is not collided, it is e to the power minus t by tau c, and probability that it is going to collide in the next differential amount of time dt is dt by tau c. Okay, and hence I can calculate the total work done. Okay, I have calculated from each collision. So delta Wt I take, and then this is the probability not collided and is going to collide. And now this time could be varying from 0 to infinity. All right, so then it's a simple integration. This E square T square by 2M tau C I take out, this tau C. And then inside I get this T square here and e to the power minus T tau C and dt. Now, this is a standard integral. I can use standard integral. In fact, you have seen this integral in my first home assignment itself. The x to the power n e to the power minus ax dx is n factorial by a to the power n. Okay. So here, of course, n is equal to 2. Okay. And hence, a is equal to 1 by tau c, and so this will be n plus 1 by tau c 3, and this is n is equal to 2. All right, this integral 0 to infinity, and that is simple e squared tau c squared by n. So that is the work done lost because of collisions for all times. Okay, so now the rate of collision. What is the rate of collision? That n by tau c. That n number is this from only one, right? But there are n electrons. So rate of collision is n by tau c. So recall that, of course, we just calculated that n squared tau c by m is sigma, and hence I just multiply this delta w into rate, okay, delta w, and then identify sigma here, n squared tau c by m, and that indeed is sigma e squared. So power lost is sigma E square. Okay. And so the power lost is joules per second is sigma E square. If I multiply into volume, then I into V, I square R. Okay. So we have had a quick review of the both the macroscopic description of the current carrying conductor from point of view of Ohm's law, and the kinds of effects that microscopically it gives rise to, and there is a connection. We will Now shift our um, focus on the battery part and the field E. Okay, this is the whole point, is to be able to distinguish between the role of the source of EMF and the E in the flow of the current. Okay, so